So now we solve one numerical based on the elastic settlement for Schmertmann method. Let us consider a footing resting at 2 meter in a granular medium, and you'll find that the gamma value which is uniform, but the top portion is unsaturated, maybe the moist, so it is gamma is 16.5 kilonewton meter cube, and gamma dash which is submerged, so directly the value is given as a submerged unit weight 8.5 kilonewton per meter cube. This is especially a granular medium, and you can see now the size of a footing is a square, and it is a big size, let us say 8 meter. Okay. This strata, though we say it is a uniform, but because of its the depth increasing, the depth, so therefore the densification is there, and E value also changes accordingly. So a profile of 20 meter is given, which is either obtained by SPT test, or it is by the, as it is a granular, so most probably the SPT values are converted into the E value. But this time this is a table for a QC value. QC value is a SCPT test, that is the static cone penetration test. Okay, so in this test, a cone is uh, inserted, which is hammer for a different blows, and we get the sorry, this is a static test, so therefore cone is continuously compressed, okay, gradually, so we get a head resistance, which is a QC, and it varies according to the depth. Okay, so QC value is 3600 is kilopascal. It varies up to 10,000. This shows that the strata densification increases, and therefore this E value also increases. Okay, especially given here that it is the E value which is obtained from the results of the SCPT test, it is 4 times QC. Otherwise, as we discussed earlier, this value can be directly taken as a something 2.5 to 3.5 times QC. Okay, so here one more thing is given, which is the time, that is the 3 years. Okay, elastic settlement, though we say it is a immediate settlement, okay, but it also gradually increases, okay, and the curve become asymptote after the passage of time. So this value after 3 years, suppose we calculate, then in that case the elastic settlement is slightly improved. Okay, so this effect is taken in the expression. Okay, so to solve this problem, okay, using the Schmertmann method, so we have directly the expression determine the elastic settlement. These are the two factors, C1, C2. So these two factors depends upon one is either the depth, second is of the discrete, and where this time is required to introduce. Okay, in this expression you will find that these two terms, it has a summation over to 0 to 2b or 0 to 4b, as we discussed earlier. Okay, so why this is required? Because the strata is varying over the depth, so therefore this influence factor and E value both are changing as per the depth. Okay, and this represent a individual depth, means depth, different depth. Okay, And this depth not only depends upon the variation of this data, also it depends upon the is influence factor diagram. So in this equation, this qn is basically a contact pressure. If it is not available, then we can also consider as a net ultimate bearing capacity. Then iz is nothing but how the settlement varies, okay, which is given by another influence factor, and this is the average over each delta z. Okay, so similarly, ez is the modulus of elasticity, okay, in that particular depth delta z, and delta z is the thickness of layer. Okay, so in this expression we are going to evaluate separately c1 c2, then average of this ratio, that is I upon e, okay, over the different depth. Okay, so now we process for the further part. Now how to work out this, we can uh, separate this into a different steps. So first we draw the influence factor diagram, that is for finding this iz, its regular values for each layer and a maximum value. Then we'll divide the entire stratum into the layers, and then we do the tabulated calculation particularly for this summation and this ratio, that is iz upon ez over the 0 to 2b if it is a square or circular, or 0 to 4b if it is a strip footing. Alright,